Hey, welcome to The Explainer. Today we're going to crack open a classic physics puzzle from Irodov's famous problem book. It's problem 1.145, and yeah, it looks a little scary at first, but it's actually the perfect way to show how a simple, clear method can help you solve pretty much anything.
You know, if you've ever felt like your head is spinning just looking at a problem with objects going in circles, trust me, you are not alone. It can feel really confusing with all the forces and accelerations going in different directions. So, here's the plan. We're not just going to hunt for an answer today. We're going to build a solid, step-by-step method, a blueprint really, that you can use again and again for problems just like this. All right, let's get into it. Here's our roadmap. We'll break down the problem, pick our physics tools, draw a picture of what's happening, turn that picture into math, and then finally, get our answer. Simple as that. First things first, we have to really carefully read the problem and pull out all the key pieces of information. I can't stress this enough. Getting this part right makes everything else so much easier.
So what's the picture here? Basically, we've got a chain, and it's spinning around in a horizontal circle, held up by a string that's at an angle. If you've ever seen a conical pendulum in a science class or a museum, it's pretty much the exact same setup.
Okay, perfect. This is one of my favorite first steps. Just laying everything out in a simple table like this cuts through all the words. On the left, we have what we know, our givens. On the right, our targets, what we're looking for. The problem just got a whole lot clearer, right?
All right, now that we know what we have and what we need, it's time to open our toolbox. What fundamental physics principles are actually running the show here?
It all comes down to good old Newton's second law. The net force equals mass times acceleration. But, and this is the big but, because our chain is moving in a circle, that A isn't just any acceleration. It's a very specific kind, centripetal acceleration. That's the acceleration that's always yanking the chain toward the center, forcing it to turn. Now this is a super important point, so let's be clear. Centripetal force is not some brand new force you draw on your diagram. It's the result. It's the net effect of all the real forces, like tension and gravity. Our job is to figure out which real forces add up to create that inward pull. And that brings us to the #1 mistake I see students make. There's this massive temptation to draw a centrifugal force pulling outward to kind of balance things. Don't do it. You have to resist. In this frame of reference, it just doesn't exist. We only draw the real physical forces we can point to.
All right, time for what I think is the most powerful step in all of physics, the free body diagram. This is our visual blueprint. If we can draw this picture correctly, the problem pretty much solves itself. The rest is just algebra.
So let's build this together step by step. First, what forces are acting on the chain? Well, gravity, of course. The Earth is pulling it down with a force of mg. Easy. Then, we've got the thread pulling on it. That's our tension, T. But since T is at an angle, it's kind of doing two jobs at once. It's pulling up and it's pulling in. So we break it into two pieces, or components. A vertical piece, T cos theta, and a horizontal piece, T sin theta.
Okay, the blueprint is done. Now, we're going to translate this beautiful picture into the language of math. We'll use Newton's second law once for the up and down direction and once for the side-to-side direction. This is where that diagram really pays off. Let's look vertically first. Is the chain flying up into the air or crashing to the floor? No. So the vertical forces must be perfectly balanced. The upward pull of T cos theta has to exactly equal the downward pull of gravity, mg. Now what about horizontally? Well, here the forces are not balanced. There's only one horizontal force, T sin theta, and it's pulling inward. That unbalanced net force is our centripetal force. It's what's causing the circular motion. And look at that. We have two simple equations, and we have two things we don't know, T and R. The physics work is officially done. All that's left is a little bit of algebra, which is the fun part, right? Finding the tension is kind of the low-hanging fruit here. If we just look at our first equation, we can get T all by itself super easily. We already know M, G, and the angle, so we just have to shuffle it around a bit. Now to find R, we can use a really cool little trick. Watch what happens if we take our second equation and divide the whole thing by our first equation. The tension, T, on the top and on the bottom, poof, it just cancels out. This leaves us with a really clean equation to solve for our last unknown R.
We've got our formulas. We've done the hard work. Now for the satisfying part. Let's grab those numbers we wrote down way back at the beginning and plug them in.
So we run the numbers and we find that the tension in the thread is about 5.0 newtons. That's the amount of force that little thread has to exert to keep the chain from flying off. And what about the distance, the radius of the circle? It comes out to about 8.0 millimeters. I mean, think about that for a second. That thing is spinning really fast, but in a teeny tiny little circle.
Look, the final numbers are great, but they're not the real takeaway here. The real prize is this 5-step blueprint. Deconstruct, strategize, visualize, formulate, and solve. This isn't just for this one problem. This is a logical flow you can use to tackle almost any dynamics problem with a lot more confidence. So before we go, here's a little challenge for you. Using the equations we just came up with, can you figure out what angle would make the tension in the thread exactly double the chain's weight? And here's a tougher question. Is that angle even physically possible? Think about it. Thanks for digging into this with me.